Hello everyone. I am your virtual host from geoengineer.org. I am pleased to introduce you to March's 2019 online lecture, organized by the International Society for Soil Mechanics and Geotechnical Engineering. This month, Dr. Wesley will be talking about what to teach or not to teach, from theory to practice. Dr. Wesley's career as a geotechnical engineer covers 8 years with the Indonesian Public Works Department, 5 years with the New Zealand Ministry of Works, 11 years with Auckland consultants Tonkin and Taylor, and 18 years as a lecturer at the University of Auckland. He has had wide experience of residual soils and has published numerous papers on this subject. His textbook Fundamentals of Soil Mechanics for Sedimentary and Residual Soils was published by John Wiley & Sons in 2010. Enjoy the lecture.
Well, good morning, good afternoon, good evening or good night, whatever the time is and wherever you may be when you happen to watch this presentation. I'm recording this in Auckland in New Zealand where I live. It's about 9 AM in the morning of the 7th of February 2019. Some general remarks I want to make. The background to this presentation is firstly that some years ago I was invited by Carlos Santamarina to contribute to a discussion he was promoting on the teaching of soil mechanics. The second point I want to make is that my career up to the age of 50 has been as a geotechnical engineer. At the age of 50 I moved to Auckland University. As a geotechnical engineer I worked in Indonesia, New Zealand and Malaysia. The climate in those countries is either wet tropical or wet temperate. And the soils predominantly are fully saturated clays, more often residual than sedimentary. My impression of soil mechanics teaching is that as far as basic concepts or principles are concerned, it is rather in a rut or has become somewhat fossilized. In other words, the core material has not been subject to the thorough scrutiny it ought to have received over the past 50 or so years. So that's just a comment on the fact that the technical content of taught soil mechanics tends to be the same today as it was 60 years ago. Is it in a rut? I think one of the reasons for this rather static situation is that university teachers are often PhD graduates who move straight on from their PhD research to become university lecturers or professors. They are naturally keen and capable researchers, and once in their new position, their prime objective is to advance their research interests and indeed to advance their careers. Their line of research often continues that which they studied during their PhD thesis. This means that they are not subject to the teaching or the learning experiences which geotechnical engineers are subject to when they encounter a great variety of real soils in their workplace and are stimulated to think more critically about what they learnt in their undergraduate courses. My experience in breaking in or mentoring new graduates while working in government agencies or for a consulting company is that they generally have a fairly good grasp of methods but a weak understanding of the concepts and especially the assumptions behind those methods. This reflects both the natural inclination of engineers, which is to design and build things, and the wish of employers, who want new graduates to immediately produce productive work. I think the concentration on methods also reflects the fact that much engineering teaching, especially with large classes, is more akin to what I call production line knowledge transfer rather than true education. So let's move on to some topics. Geotechnical engineering and soil mechanics are not the same thing and should not be confused. Soil mechanics is a theoretical discipline. Geotechnical engineering is a practical undertaking more akin to a profession. It involves many components: soil mechanics, geology, observation, experience, and a judgment. That's just a portrayal of geotechnical engineering and its components. The solid foundation for geotechnical engineering is obviously soil mechanics, but the other ones that I've listed there are important. And I think we need to emphasize the importance of visual observation more, that To become a good geotechnical engineer, you should be taking every opportunity to observe the way soils behave in the field, especially looking at cuttings and places where the soil is exposed. The role of universities is to teach soil mechanics and to be sure that what they teach is relevant to geotechnical engineering. Some further thoughts. The predominant aim of university teaching is to produce graduates in civil engineering, only some of whom will become geotechnical engineers. Whether they become general civil engineers or structural engineers, it is still important that they have a reasonable grasp of basic soil mechanics. Structural engineers should at least be able to ask the right questions when seeking soil parameters to put into their computer analysis. As I've said, graduates are generally strong on methods, but weak on their understanding of basic concepts and the assumptions involved in the methods that they use. A point of relevance here is that teaching soil mechanics is in a sense straightforward and obviously is the prime role of universities. Relevant to geotechnical engineering is very important, and universities are not well equipped to meet this goal simply because there are very few staff members in universities these days who have actually done any geotechnical engineering in practice. Professor Jean-Louis Briard, when he was the president of the International Society, made the comment that teachers of soil mechanics should have worked at least 5 to 10 years in practice before taking on the teaching job. This is unlikely to happen. Universities are clearly putting much more emphasis on research output than on the quality and relevance of its teaching. These topics that I'm going to look at here are simply ones that I've come across that I think I particularly want to make comments on. One is the order in which material is presented in courses, the issue of residual soils, a little on terminology, analysis using total stress and analysis in terms of effective stress, soil classification and description, the seepage state and the pore pressures in the ground, compression and consolidation behavior, and the limitations of theory, and some comments on compaction control. Most soil mechanics courses begin with soil composition, particle size, atomic limits, clay minerals, classification systems, etc. And this material, while obviously essential, is unlikely to be interesting or stimulating to undergraduate students, or any students for that matter. So why not start our lecture courses, the Introduction to Soil Mechanics, with something more likely to be more attractive to students and less likely to create the impression that soil mechanics is a somewhat dull, boring subject. The core concept or principle at the heart of soil mechanics is, of course, the principle of effective stress. So, surely the first lecture should be on this principle. And students should be encouraged to understand that the principle is not something new, but something they are already familiar with from their own experiences. The physical concept should be introduced ahead of the equation that expresses it. And this is Tertsagi's formulation of the principle, so it's the first sentence here that is important, the concept, not the formula, but the concept. When stress is applied to a fully saturated soil, it will be resisted by either the soil particles or the water, or shared between them. And we're all familiar with that simple equation. The effective stress is by definition the stress that actually acts on the soil, and changes in volume change of the soil only occur if there's a change in effective stress. Change in volume or strength will only occur if there's a change in effective stress. It is preferable to explain the concept of the principle of effective stress before introducing the simple equation. One way of doing this, and at the same time relating the concept to a simple situation the students are already likely to be familiar with, is shown in the next slide, which is the way we begin the first lecture of the first paper in soil mechanics for our students at Auckland University. So what I ask the students to do is think about a little experiment. You've got a tin can as shown. It's empty, it's got a lid on it, sealed, and you've got a sponge, and you're progressively adding weights to both of them And the question you've got to answer is, what happens? Nothing, compression or collapse. And they'll come up with the right answer. The tin will compress and collapse. The sponge will just continuously compress. Now we change the process by which that stress on both of them is applied in a totally different way. We've got them fastened to the bottom of a large tank, and we're going to steadily raise the water level in that tank. And the same question is asked. We've got the sponge and we've got the tin. And give the students a little while to think about it, and generally somebody or most of them will come up with the answer that the tin will again compress and collapse, but nothing will happen to the sponge. They can sense that a sponge is full of water, and the pressure coming from the rising water level is resisted by the water within that sponge. And it's then quite useful to go on and talk about the concepts of undrained and drained behaviour, but first just to relate the behaviour of soil to that of the sponge. So at the top there, whether the material consists of boulders or sand or clay, whether the water level is a few centimetres or a few kilometres, nothing happens to those materials because they feel none of that stress. It's taken entirely by the water filling the voids within the material. And then to give an illustration of undrained and drained conditions using the analogy at the bottom. We've got a soil sample in a container and a membrane separating it from the water above it. We've got the ability to measure the pressure and the pore pressure in the soil, and we've got the ability to open that valve and let the water flow out. And in the example on the left, we've got the taps closed, so what will happen as we raise the water level? The dial gauge there will record an increase in stress exactly equal to the stress coming from the rise in the water level. And then we can talk about what happens if we open the valve. And again, what happens depends very much on the permeability of the soil. Clearly water will flow out, and the reading on the gauge will start to decrease. But the important point is that the rate at which the water can flow out governs whether the soil behaves or in a drained or an undrained state. It's important to recognize that undrained behavior will occur dependent on two conditions. Obviously, if there are no outlets, if it's totally sealed and no water can escape, then behavior will be undrained. But equally true, if the permeability of the soil is very low and the load on it is applied rapidly, there won't be any time for the water to escape. So the behavior will again be undrained, not because there are no outlets, but because there is not time for the water to escape via those outlets. Examples of the practical application of the principle of effective stress. I like to start off with this one, just the effect of lowering the water table and working out how much compression will occur in that clay layer shown there. We have to introduce the simple relationship between compressibility and the applied stress using the linear parameter mv there, which is given, and make the assumption that the simplicity will assume that the unit weight of the sand remains the same as the water level is lowered. So by working out the effective stress at the center of the clay layer, the students will find out that the effective stress increases and causes a compression of that clay layer, which can be calculated using the simple relationship I mentioned between compressibility and the applied load via that EMV parameter. Another example is just to think about the stability of a concrete dam sitting on a porous foundation, sandstone or some type of material through which water will seep, and to explain that it's not a simple case of multiplying the weight by the coefficient of friction, because beneath that concrete block there is an uplift pressure coming from the water seeping beneath it. So the true safety factor will be given by those formulas at the bottom there, and perhaps introduce to the students the idea that in soil mechanics the frictional component of strength is expressed as an angle rather than as a coefficient of friction. Another example is, why do slips occur in hillsides during periods of heavy rain? Simply because the phreatic surface or the groundwater level rises, causing an increase in pore pressure and a decrease in the effective stress across that plane, which means a decrease in strength. as explained in that picture. And lastly, move on to a simple, probably the simplest measurement of soil shear strength is to measure the strength in a simple triaxial test, an undrained test where you've got a membrane around the sample, and explain to the students what happens, that the strength of the material remains the same no matter how high that water pressure is in the cell, simply because it's resisted by the water in the pore space of the samples, and you get a constant strength. And that will be, I think, in Auckland University, that is the first experiment that the students do. A much more interesting experiment than starting off with measurements of specific gravity or at big limits. Moving on now to residual soils. Soil mechanics grew up, residual soils appear to occupy more of the world's land area than sedimentary soils. Soil mechanics grew up in Northern Europe and America from the study, as we all know, of sedimentary soils, often from artificially created or remolded sedimentary soils. So the behavioral framework, or the theoretical basis of soil mechanics, is derived almost entirely from the properties of sedimentary soils. Textbooks and geotechnical engineering courses or soil mechanics courses deal almost exclusively with sedimentary soils, even in countries where residual soils dominate. Two important points. The first, most of the basic concepts and principles in soil mechanics are equally applicable to sedimentary and residual soils, those that I have listed there, but there are some very important differences. It's well past the time that residual soils should be an integral part of mainline soil mechanics, especially in university courses. But this does not mean great changes or special lectures for residual soils. It means highlighting the differences in behavior as appropriate throughout lecture courses. If you have a look at my book, Fundamentals of Soil Mechanics for Sedimentary and Residual Soils, that is what I have done there, simply highlighted the difference as they arise in whatever aspect of the subject one is covering. That's the picture which students should be familiar with. Chemical weathering converts rock to a soil. It's generally eroded, transported, and ends up in a sea or lake, and that forms a series of more or less horizontal layers of what are sedimentary soils. You get uplift, and that gets lifted well above sea level, so you get plenty of sedimentary soils on dry land. So that's the minimum that students should understand about residual soils. Principal differences. Residual soils do not undergo the sorting process created by erosion and redeposition, and thus are much less uniform than sedimentary soils. That transport process and redeposition means you tend to get all the fine material in one place and the coarse material in another, so it is a sorting process which doesn't occur with sedimentary soils. Because they are not created by deposition and consolidation, stress history has no relevance to residual soils. That index, the compression index CC, cannot apply to residual soils, because by definition it is the slope of the virgin consolidation line, and residual soils have no such line simply because they weren't formed by a consolidation process. Empirical relations developed from the study of sedimentary soils may not always be valued for residual soils. Residual soils are generally of much higher permeability than sedimentary soils, which is quite an important point, especially in relation to the influence of rainfall on the stability of slopes. Talking about soil classification and description, it's not a subject that greatly enthuses students. However, at least they should know what the terms clay and silt mean and the difference between clay and clay fraction. Clay is a material that has the properties of cohesion and plasticity. It can be manipulated or molded without cracking or volume change. Clay fraction is the proportion having particles of clay size, which may be quite small. You only need to have 15 or 20% of genuine clay material before it will influence all of that material to act as a clay rather than as something else. Silt has these properties of quick behavior when you vibrate it. It's like liquefaction of sand really. When you vibrate it, water will start to emerge at the surface and cause it to become shiny. Then if you squeeze it again, it dilates and the water is drawn back into the sample. They should understand why we have Atterberg limit tests, which is basically because particle size of a fine material is not a good guide to its properties. That's why Casagrande looked around for something else that would be a better guide and developed his Atterberg limit tests. They should also know the basic principles of the unified soil classification system. As illustrated here, the material is divided into coarse grained and fine grained on the basis of particle size, the proportion greater or less than 0.06. The separation between fine-grained and coarse-grained soils. The coarse-grained soil is then divided into sand, gravel, or boulders on the basis of its particle size, whereas fine-grained soils, particle size is no longer required and no longer used as a basis for dividing it between clay and silt. It's the behavior of the material, whether it shows the characteristics of a clay or whether it shows the characteristics of a silt. As I said, particle size is not used to differentiate between silt and clay because it is no longer a guide to their behavior. In its place, the manipulation tests or Atterberg limits are used. By manipulation tests, I mean the vibration test and the dilatancy test that we use for distinguishing silt and clay. And I want to emphasize the usefulness of Atterberg limits, dealing of course with clays here. You get two useful pieces of information from Atterberg limits. One is the position of the soil on the plasticity chart. That indicates the type of material it consists of, what I've called here its inherent properties. The second is, as long as you know the natural water content as well, the relationship of that natural water content to the liquid and plastic limits, which we define by the liquidity index, indicates the compactness state of the soil. In other words, whether it's in a dense state or a non-dense state in the ground. So firstly, looking at the usefulness of the plasticity chart. If you're in countries where there are volcanic material of volcanic origin, the chart is not useful for classifying them. A very common soil in countries which have volcanoes, particularly andesitic volcanoes, are volcanic ash soils containing this unusual clay mineral allophane, and they plot well below the A line. But their behavior is not the behavior of silt. You can do those tests and you'll find that they are much closer to clays than to silt. They don't show the characteristics of silt at all. Similarly, the tropical red clays containing the mineral halloysite tend to plot along the A line or a bit below it. Again, they are definitely clays, they are not silts. Another group that's quite well known are what are called black cotton soils, or just black soils. They're high in the clay mineral montmorillonite or smectite, and they've got very poor engineering properties. So the usefulness of the chart is this, that it gives you a good guide to the sort of properties you can expect from that soil. If it's plotting well above the A line, you've probably got a problem soil. Low shear strength, high compressibility, strong tendency to shrink or swell during moisture content changes. If it plots below the A line, well below the A line, you can generally expect it to have high strength, low compressibility, and not show much in the way of swelling or shrinkage properties. So that's the usefulness of the plasticity chart as an indication, as a broad indication of the likely properties. This is just a couple of examples. These are the rice fields in Java or Bali. They consist primarily of the weathered volcanic ash, and they remain stable at angles of up to about 40 degrees, even though they are fully saturated. You've got a canal at the top feeding water into those terraces. It flows from the top terrace down to the bottom terrace and keeps the rice alive on the way down. When the plants are quite mature, then the need for water is not so great, but certainly when they're planting and growing, the water has to be supplied or the rice simply won't develop. As I said there, they can be stable on steep slopes up to 35 or 40 degrees with a continuous supply of irrigating water, and they predominantly consist of allophane clay or halloysite, which plot well below the A line. In contrast, have a look at this one here. This is a flat area where the weathering process produces these black cotton clays, or these black clays, very predominantly with the clay mineral montmorillonite. And there you've got a very gentle slope, but you've still got a slope failure on a very gentle slope. As I've said there, this is in East Java, Indonesia. The soil is of the black cotton variety, coming from old shales, high liquid limit, well above the A line, containing montmorillonite. Moving on from the usefulness of the plasticity chart, I'll just make these comments. Classification using manipulative tests, moulding, shaking, dilatancy, must take precedence over the plasticity chart for distinguishing clay from silt. The H and the L in CH, CL, etc. mean high and low liquid limit. They don't mean high or low plasticity, as is often assumed. MH, clay of high plasticity, could not mean a silt could not mean a high plasticity silt. If the material was of high plasticity, it would be a clay. The plastic limit is actually very useful in quality control of compaction involving medium to high plasticity clays. The plastic limit, particularly for medium to high plasticity clays, is very close to the Proctor optimum value. And it's very easy to do a plastic limit test to tell you whether the soil is wetter or drier than the plastic limit. You've only got to find a surface on which to roll out a thread of the soil, and it'll tell you whether you're compacting that soil above or below the plastic limit, meaning above or below the optimum water content. So coming on to what I've called here compactness indexes. We've got one for sand, which you're probably very familiar with, the relative density. It is a measure of the denseness or the compactness of the material. And for clays, we've got the liquidity index, relating the position of the water content in relation to the plastic and the liquid limit. If you've got a material with a water content close to the plastic limit, it is in a dense state. It's very unlikely to ever show a yield pressure. It's sufficiently dense that when you apply a load to it, it will just make it more dense, and you won't find any sort of a yield pressure in it. You won't have any problem doing earthquakes if your water content is way down here or your liquidity index is low. If you've got a material with a water content up around the liquid limit, that in itself does not tell you whether it is in a strong or a weak situation in the field. There are plenty of soils with water contents close to or above the liquid limit that in the natural state are quite strong. What it is telling you is you've got a material in a non-compact state. If you disturb it or remold it, you're likely to destroy its structure and release water and make it very weak. But it's not telling you what its in situ strength is likely to be. So to interpret the meaning of your liquidity index, you need to have an additional piece of information. What is the undrained shear strength of the material in its natural state? And then you'll know what sort of a material you're dealing with. And this is just emphasizing the point I've just made. It's normally accepted that the undrained shear strength at the plastic limit is somewhere between about 170 and 200 kPa, and it drops by a factor of 100. So at the liquid limit, if it's 200 up here, it will be 2 kPa down here. And this graph is more or less the relationship for the disturbed material. If you convert it to a log scale, it comes out to be pretty close to a straight line. I've plotted it on a linear scale so that it gives you a true impression of how rapidly your strength decreases when the water content rises or falls below the plastic limit. And these are just three particular soils that I happen to have some information on. Volcanic ash soils can have water contents above the liquid limit and yet still have an undrained shear strength of around 100 kPa. Now, weathered sandstones around Auckland generally are a fairly low liquidity index, but there are some with a fairly high value and are quite sensitive. Tropical red clays. the water content is generally close to the plastic limit. So they sit somewhere up here. But what you know is that if you're doing earthworks or anything else that's going to disturb these soils, then you're going to have a problem because they're going to soften very rapidly. And soils which plot out here with natural water contents above the liquid limit, they've got a fairly fragile structure, so they're likely to show a yield pressure when you do a test on them or simply apply a load to them in the field. There will be a certain stress level at which that fragile structure starts to collapse, and you'll get a yield pressure from those. Just a note on the importance of micro soil structure. Most soils have some sensitivity, that is, they lose strength when disturbed or remolded. The property that gives them more strength when undisturbed than after remolding is their in situ structure. This may be bonding or cementation between particles, or some sort of interlocking mechanism. In their undisturbed state, some soils are quite firm or strong, even though their natural water content may be as high or higher than their liquid limit. If I was investigating a particular soil that I had no information whatever about for the first time, apart from visual observation, the most useful test items of information would be the natural water content, the Atterberg limits, and the undrained shear strength. If I had that information, I'd have a pretty fair idea of what sort of a material I would be dealing with. Just a note on methods of stability analysis, particularly, do we do our analysis in terms of total stress or in terms of effective stress? Many students complete their undergraduate degrees with only a vague understanding of the shear strength of soils and with an inadequate grasp of the basic methods of stability analysis. I think the situation is linked back to not really appreciating the implications of the principle of effective stress. With respect to shear strength, students should understand that there are two separate and equally important ways of measuring and expressing shear strength. One is the undrained strength. The second is the strength in terms of effective stress expressed by that well-known equation. As far as the undrained strength is concerned, we don't need to know what the stress is acting on the soil. But if we're doing an analysis in terms of effective stresses, we need to know the total stress and the pore pressure so we know what the effective stress is in order to use that equation there. So there are thus two distinct methods of estimating stability, whether it's a foundation or a retaining wall or a slope. An undrained or total stress analysis based on the undrained shear strength, or an analysis in terms of effective stress based on the effective stress parameters C and phi prime. The latter is sometimes called a drained analysis, but this is not correct. An analysis in terms of effective stress makes no assumption about whether the failure will be drained or undrained. And I think, as we all appreciate, an undrained situation can be analysed in terms of effective stress. The next slide is a simple illustration of when to use a total stress analysis and when to use an effective stress analysis. I'll not read the rest of this slide because I'll explain it by looking at the following diagram. So we've got a level site of clay water table up near the surface somewhere, fully saturated clay. We're doing two quite different things. One is we're putting a building on the surface. The result of putting that building on the surface is, with time, consolidation is going to occur and the strength of the soil will increase with time. So if we make our estimate of bearing capacity using the undrained strength, we are certain to be safe. We can't be sure how long it's going to take for any increase in strength to occur, so the safe way to design the foundation or to estimate the bearing capacity is to use the undrained shear strength. However, on the right-hand side, we've made an excavation which has the opposite effect. Removing that amount of soil is going to greatly lower the pore pressure around this excavation, with the result that water is going to flow with time towards that excavation. You'll develop a new water table, a new phreatic surface on each side of the excavation, assuming that we're pumping or we've got some means of keeping that excavation dry. So with time, the strength of the soil is going to decrease. So we can't estimate the stability or judge the stability of these cuttings using the undrained shear strength. the only safe way is really to revert to an analysis in terms of effective stress and make an assumption about what the final phreatic surface is likely to be, and measure the values of C and phi so you can do an analysis in the terms of effective stresses. Bishop coined the terms end of construction case and the long-term case. So the end of construction case is the situation where your material still has the original undrained strength because there hasn't been time for water to flow out of it. So the end of construction case you can base on the undrained strength, but the long-term case you have to think about, is the strength going to decrease or increase with time after you complete the project? Some issues regarding shear strength. Students are slow to grasp the concepts involved, and considerable repetition is needed before they have an adequate understanding. The case of the undrained strength is straightforward. The diagram there shows you the normal result from a series of undrained triaxial tests at different cell pressures. Note that this is not the behavior of a clay as distinct from a sand. You'll get exactly the same result provided these two conditions are met: that the soil sample is fully saturated and the test is undrained, and you'll get the same result whether it is a clay or a sand. And I think we're familiar with this situation here. If you did measure the pore pressure in your undrained tests, subtracted it from the total stress, you would find you would only get one circle in terms of effective stress, the dotted circle here. To determine your C and phi values, you would need to do consolidated undrained or drained tests in order to establish that line there. A question does arise: should an analysis using total stresses and effective stresses or effective stresses give the same answer? And if not, why not? Probably not many geotechnical engineers can answer this question, so perhaps it is unrealistic to expect students to be able to. One way of answering the question is to consider a possible shear plane somewhere in the ground, and we've got these stresses acting on it, total stress. We measure the pore pressure, we can estimate the total stress, so we know what the effective stress is. We measure our C and phi, and so our computer program or our manual analysis, we will know the value of the effective stress, and applying it to that equation, we can read off here the strength in terms of the effective stresses. So that is the strength we would get there if we were doing our analysis in terms of effective stress. If we were going to do it in terms of the undrained strength, we would have to do a measurement of it. So we could perhaps somehow do the measurement in the field by taking this sample here to failure, but in the process of doing that, we will inevitably change the pore pressure state. It will either rise or fall. Or we could very carefully sample the material and set it up in a device in the laboratory and carry out the test in the laboratory, of course as an undrained test. And in the course of doing that test, again, we would raise or lower the pore pressure. So assuming that we cause an increase in pore pressure, we are reducing the effective stress by that amount there, and this will be our undrained strength here. So for that reason, we cannot expect an analysis in terms of undrained strength to give us the same result as an analysis in terms of effective stresses. Another way of looking at it is to think about stability analysis using a slip circle analysis. If this is our potential slip surface here, if we did our analysis in terms of undrained shear strength, we would probably use the same value all the way around here. Whereas if we did it in terms of effective stress, we would generally find that the effective stress here and here, where the total stress is very low, is much less than the value of effective stress at the middle here, where the total stress is much higher. So our strength profile is likely to be quite different when we do our analysis in terms of effective stress compared to doing it in terms of total stress. Now, something on the seepage state and pore pressures in the ground. There's a serious flaw in the way permeability and seepage are taught in most, if not all, university soil mechanics courses, and indeed in textbooks. Students leave university erroneously believing that the water table or the phreatic surface is the upper limit of the zone of seepage flow. This can only be true with sand. It can't be true with clays, with the latter capillarity keeps the soil above the water table fully saturated, possibly for tens of meters above the water table. Perhaps a quick review of some relevant physics will remind students of basic aspects of the behavior of water. Think about taking a cylinder, like a cylinder that you do a hydrometer test in, submerging it in here so that it's full of water, turning it upside down and pulling it upwards. Let's imagine our cylinder is of unlimited extent. How high can we pull this cylinder and it will still remain full of water? And generally, you'll get a student will come up with the correct answer of about 10 meters. By the time you get 10 meters of water, you've reached atmospheric pressure, and you'll have a balance between the pressure at the bottom of the cylinder and here, and you'll find you've got air in the top there. So that's one feature of soil behavior. Relating it to soil, not quite a direct comparison, because soil is not sealed at the surface, but soil has this thing called an air entry value, which is like a sealed surface. It takes a very high air pressure to force air into the soil. So in a very real sense, a column of soil is rather like a closed cylinder, simply because of this very high value of air pressure needed to force air in amongst the particles. And then to have a look at what happens where you've got a series of open tubes of different diameter, and as illustrated there, the smaller the diameter, the higher the water level will rise. And that level to which it rises doesn't depend on having a nice tidy tube. You can have a tube in all sorts of shapes and sizes. As long as it ends up at this level, that's where the water level will be. So that's the situation with regard to soil. Soil has got a very tortuous route amongst all its particles between the water table and the surface, but the same principle applies. So what in fact is the water table? There are various options listed there. Certainly it is the same as the phreatic surface. Is it a line below which seepage is occurring and above which there is no seepage? Is it a line below which the pore pressure is positive and above which it is zero? Is it a line of pore pressure where the pore pressure is zero, i.e. atmospheric? The answer is, in coarser materials, it is a dividing line above which no seepage is occurring. In clay, it is simply a line of zero pore pressure. It's not a discontinuity in the seepage pattern or even in the pressure state if we're talking about a static situation. Seepage occurs above the water table according to the same laws as below the water table. So looking at the static situation, that's just the normal portrayal. You've got a water table here, and looking at the likely zone of full saturation for different materials, if it's a low permeability clay, like London clay, you're likely to have fully saturated right up almost to the surface. There may well be a zone of partial saturation here, not because water drains out under gravity, but because of evaporation from the surface. If you've got gravel or something, there may be if it's a clean sand, you may have a very low capillary rise here, so your zone of full saturation is almost the same as the water table. And for intermediate materials, your zone of full saturation may be somewhere in between here. The only static situation pore pressure state, I should say, in this situation is this one shown here. Your pore pressure will be positive hydrostatically below this water table, and it will be hydrostatic again but negatively above it. Any other situation than that is not a static one. It means drainage will be occurring or seepage will be occurring. If you had zero pressure between here and the surface, you would have a hydraulic gradient of 1 from here down to here, because your change in head would be the same as the change in length. So if you're going to have a zero pore pressure down here, you've got water seeping from the surface down to here and a hydraulic gradient of 1, because the head change is the same as the distance change. Seasonal effects. Pore pressure state is actually never or very rarely static. It varies daily with changes in seasons or the weather. And it's important to recognize a fundamental difference in the way pore pressure changes occur in a granular material, sand or gravel, to a clay. In a granular material, if we were lowering the water table, water would drain from the pore space and be replaced by air, and there's very little or no significant volume change. The phreatic surface is the upper boundary of seepage, and flow below the water table is still governed by the Laplace equation or Darcy's equation. And the parameters governing the changes with a sand or gravel are the permeability and the porosity. The permeability governs the rate at which water can get out. Porosity governs the volume of water that would drain out of the pore space. In clay, water drains from or into the soil as a result of volume change, not because of movement of water to be replaced by air or the other way around, and the soil remains fully saturated. Flow is governed by the equations for transit flow, and the governing parameters now are the permeability, which governs the rate at which water can drain out, and the compressibility, which governs the volume of water that can drain out, or, if you like, in the combined form, the coefficient of consolidation. So the process is very similar to the very simple case of consolidation that to which the Terzaghi equation applies, and which we are mostly familiar with. Just emphasizing the point I've just made, if you had a situation where there'd been some dry weather and your water table was down here in a granular material, you get rainfall, it trickles down through the space here and fills it up, and your water table rises, and you've got a hydrostatic situation below the water table. With clay it's totally different. If it's raining at the surface will start to soak up water and it will swell, and that process will steadily move deeper down through the soil layer, but at a decreasing level. So you're going to have maximum swelling at the surface, and it will steadily decline, and there will be some depth at which it will no longer penetrate. The rainfall will cease and the sun will come out. So depending on the permeability of the soil and its compressibility governs just how far down that influence will go. And that's just emphasizing the points just made. This is the case where we've got rainfall and we've got a gravel material. So the water table rises as the water trickles down and fills up the space, and the pore pressure is hydrostatic in relation to that water table. If we go to the opposite end of the scale to a very low permeability material, such as the over-consolidated clays of Britain, London clay and such like, the zone of influence of your dry weather and your wet weather will not be very deep enough. In other words, it won't penetrate as far as the water table. My understanding is that in London, seasonal effects don't alter the depth to the water table, simply because the zone of penetration is quite small. In the summer, evaporation at the surface will cause your negative pore pressure to become more negative, and in the wet season or the winter, when you've got a supply of rainfall, this will start to change down here. But there will be a limit. So I've shown here, this is the depth limit of the seasonal changes, whereas your water table down here remains constant. And then for intermediate materials, you've got an intermediate situation. You've got a limit of seasonal changes down here, but you've got your water table up here. In this case, particular example, this is your average water table here. In the summer, the evaporation causes this to become increasingly negative, so your water table will drop down to that value there. In the winter, water will seep in, and this line will tend to move in this direction here, so you're going to have another line up here. So your water table may rise to here during wet weather and fall down to here during summer weather. That's just emphasizing the point just made, that the depth of seasonal influence has got a limit to it, wherever your water table is. The deeper you go, the less is the effect of seasonal changes, and eventually they run out at a limiting depth down there. Natural seepage and hill slopes. This is the conventional, if you like, simplistic representation of the water table and the seepage state in a slope, implying no seepage above the water table. A much more realistic portrayal is the one that I've shown here. The former one indicates or implies that there's no rainfall on the slope itself, and there's a recharge zone some distance away where you are getting rainfall. But if you've got rainfall over all of the surface, then there's going to be water coming in from the hillside itself, from the slope itself, as well from the catchment beyond it. So you're going to have a seepage pattern, something like this. Some of it coming straight from the slope itself, some of it coming in from some distance away out here. And your phreatic surface will be a line which cuts across these flow lines. It won't be parallel to them, as I've shown there. And the next picture just illustrates this. If you've got a measured water table, by some means you've established a water table, you could make the assumption that this would be your flow net, which would only be correct if this material was a clean sand or gravel and you had nothing going on above that water table. A more likely flow net is this one here. In fact, if we had a double-sided hillside, in other words, if it was symmetrical about this line AB, then the only possible flow net is this one here, because anything that falls over here is going in the opposite direction. And the position of your water table will be governed by the relationship between the intensity of the rainfall and the capacity of the soil to accept that intensity of rainfall. If it's only of moderate intensity, as I've assumed here, in relation to the permeability of the soil or the capacity of the soil to accept seepage from the surface, your water table may be here. If the rainfall intensity is higher, then this will come higher up, and similarly, if the rainfall intensity is very low, this will drop further down. The shape will be pretty much the same until you get right down to having an almost level water table. So as I've said here, if the hillside is double-sided, symmetrical about the line AB, then the lower flow net is the only possible one. The position of the water table is then dependent on the rainfall intensity relative to the soil permeability. To determine the seepage pattern of a steep slope, it's actually necessary to know a bit more than just the position of the water table, simply because your pressure doesn't increase hydrostatically with depth if you've got a situation like this in a steep slope. Seepage through an embankment dam is often portrayed as in the upper graph here, quite familiar with that, but nobody would ever build an embankment dam out of gravel. This would only be true if this was clean gravel or clean sand. They would build it out of impermeable clay, in which case this is the shape of the flow net you're likely to get. It's not all that important because it doesn't greatly alter the pore pressures below the phreatic surface. It does alter the rate, as you've got a wider channel here and a different ratio of equipotential drops to flow channels, but it doesn't alter the pore pressure state below this line, but it does show that you're likely to have a negative zone above that phreatic surface. Again, you're likely to have rainfall on here from time to time, and you're likely to have sunny weather, so there's a lot going on here in a dam that the phreatic surface itself is unlikely to be particularly constant. Summary of the important points. Groundwater cannot drain out of fine-grained soils. Under gravity, surface tension behavior prevents this. Fully saturated clays therefore cannot become partly saturated from gravity drainage, only from evaporation at the surface. The water line in general is a line of zero, meaning atmospheric pore pressure, not a discontinuity. In the fully saturated zone, seepage takes place according to the same laws above and below the water table. But we note that the mechanics of a changing pore pressure state are quite different in coarse-grained soils and fine-grained soils. Just a note about drawing flow nets, just the simple case that we have a cross-section of a dam like this, a water level here, and we're going to draw a flow net. Well, this is how I teach it anyway. I always like to go for 4 channels, because then you know you're going to put in 3 flow lines here, and it's easiest to put the middle one in first, particularly to take account of curvature. Here we've got curvature coming in here, so we know we're not going to have an even distribution of points along here. So if you put your middle one in a bit closer to the center of curvature than otherwise, again down here it's going to be curvature coming into here. I should perhaps have mentioned that this is our water level here, and we're assuming we've got a water level equal to the ground level here down here. So that is a equipotential, and from here to here is also an equipotential. So these lines must be closer here than here because the water is curving in. So it's curving this way here, and it's curving this way here. Once we put those markers in, across here you see the curvature is fairly minimal, so the division should be fairly even. In fact, I think I may have got it wrong here. This one should have been closer to the middle. Anyway, then you can put your lines in like I've done here, making them nice and smooth. They should be intersecting this line at right angles, of course. That one doesn't look as if it's quite at right angles. And then you start from one end or the other and you draw in your equipotential lines as I've done here. If you then wish to determine the phreatic surface, you count your equipotential drops, 1, 2, 3, 4, 5, 6, 7, and you divide this height into 7 steps. So each step indicates one step along these equipotentials here. So in order to establish your line of zero pore pressure here, you have to extend this line along here until it meets the first equipotential. And at that point there, you have now got atmospheric pressure. Similarly, as you work your way down through here, you can establish all those points and draw in your phreatic surface. I won't go through these, or perhaps I'll go through these guidelines. Choose a scale so that all lines are complete. Examine the boundary conditions so that you know which are flow lines, equipotential lines, imperial boundaries, and potential seepage surface. And try to imagine in your mind how the water will flow. Then you set up your guide markers. I always do it for 3 flow lines to create 4 channels. Remember that the sharper the curvature, the closer together the lines must be. Sketch the 3 lines, recognizing that they should be smooth curves, except very close to the impermeable boundaries. Now begin by drawing in the equipotential lines, starting from one end. Don't start in some arbitrary way in the middle. Beginning at the end, and remember, the equipotentials should intersect the flow line at right angles and they should form squares. And you can imagine whether you're forming squares by imagining whether a circle will fit within them. Then examine your flow net and work out how to improve it where needed. That is the more difficult part of it. It requires considerable thought before you can figure out if your flow net is clearly wrong, what you need to do to improve it. One of the 3 laboratory experiments in our first soil mechanics paper at Auckland University involves the use of a seepage tank. And the students are required to, before they do the experiment, they're given the dimensions of the tank, they are required to draw the relevant flow net, and then use their flow net to estimate the flow rate, the flow paths at 3 points in the net, and the height to which water will rise in 2 manometer tubes connected to the seepage zone. So they've got quite a bit of work to do before they do the experiment. That's the tank there, the shape of the tank. So they're given a piece of paper with all those dimensions on it, and they set to and draw the flow net. Generally, we give them a pretty good indication of where the phreatic surface is going to be. This is a coarse quartz sand, or reasonably coarse. It's been chosen to have the right grading to give us acceptable times for our dye traces to travel from one side of the flow net to the other. So what they've got to do, they've got to estimate how high the water will rise in these 2 manometer points here. They're required to estimate the flow rate, so they're required to do a measurement of the rate at which water is travelling out of here, and they are to set these dye traces going and measure how long it takes for the dye to travel from here to here to see whether their estimate will be longer, of course, for this one here, because the hydraulic gradient between here and here is substantially lower than the hydraulic gradient between here and here. Now, it's a very good experiment. It's a very good portrayal of the fact that our flow nets are not theoretical concepts, but they do occur in practice. It's interesting too that once the dye trace reaches here, there's no longer any need for it to feed in from here. In fact, there's no need for it to feed in from here at all. Once you've set it going, the trace can just move around and leave behind clear space. Although we find, you see, these injection points are right at the surface of this perspex side of the tank here, that when you turn these off, the dye trace will move out. But after you've done the experiment 2 or 3 times, you can just, there's enough of the dye traces left behind, you can just see these going through here. So if you want to start with a perfectly clean sheet, you have to empty all the sand out, which is a very tedious exercise, and put the sand in out after you've got rid of all the dye. But it's a very good experiment, very useful in getting the students to do some hands-on experience and illustrate that their flow nets are not theoretical things. They are exactly what happens in practice. And in our first soil mechanics paper, our students are required to do a project, and what they need to know to do that project, they need to understand the principle of effective stress, they need to know the basic equation for soil compressibility, and they need to know how to draw a flow net and how to use it to determine pore pressures. The object of the exercise is to estimate the likely settlement of ground alongside a deep excavation. So this is an actual excavation, it's 20 meters deep. It's close to the edge of the harbour, so this water level here is fixed. That's fixed by the tide, because this is a layer of quite permeable fill here. This is low permeability clay and low permeability sandstone down here. So the students have got to draw a flow net as the water seeps from here around to here, and use that flow net to estimate the change in effective stress down through this layer here, and use those changes in effective stress and this value of EMV to estimate the settlement here. So they have to calculate the settlement at point B and at point A. And I think because this K value here is rather similar to this value here, we tell them that they must assume that the permeability is the same in order to be able to draw a flow net. We don't expect them to draw flow nets when the material properties are different. And we could also ask them to estimate the change in stress on this wall, assuming that it is a rigid wall, or making the assumption that it moves sufficient to create the active pressure here. So we could actually get the students to work out to what the pressures on here would be in order to design these retaining meshes on each side. So I think that brings me to the end of my presentation. Though that row of inclined boreholes is alongside the Leaning Tower of Pisa, and this I visited the site when they were doing the correcting measures. They had a rig which moves backwards and forwards, and here uses these spiral orders to progressively extract soil from under the high side of the tower, and they moved it back from being out of line by 4.5 degrees to being only about 4 degrees over the space of about 6 months that it took them to undertake that. Those are the references that you'll find useful. One is the original paper by Carlos Santamarina and my response to it, and you'll find most of what I've covered here in the soil mechanics book that Wesley's subject. So, thank you for attention. That is the end of my presentation. This is the second part of my presentation, and I want first to talk about the compression behavior and the consolidation behavior of clays. The compressibility is normally portrayed using a log scale for pressure, the so-called E log P plot. E is the void ratio, P is the pressure. Why the log scale for pressure? Simply because it just happens to produce a straight line if the soil is deposited underwater and consolidated by vertical pressure, or is consolidated from a very liquid state, a bit wetter than the liquid limit. Is there any reason to use this plot for a residual soil, which is created by a totally different process? The only reason is tradition, hardly a valid reason at all. However, the E log P plot is suspect even when used with sedimentary soils. It has continuously, routinely been misinterpreted and creating misunderstanding of the true compression behavior of almost all soils. Now this is how a soil behaves if you consolidate it from a slurry, which is what I've done in these two pictures here. On the left we've got it plotted using a linear scale, on the right a log scale. And you'll see it's very curved and untidy on the left, but much more tidy on the right. So that's the basis for using the log scale, the assumption that you've got a more or less straight line as your virgin consolidation line AE. Your unloading and reloading lines are assumed in textbooks or in teaching to be parallel, but if you examine them closely, they're not really parallel. But what I want to particularly point out here is if this was a soil in nature, if it got consolidated down to this point E here, a natural consolidation compression process, it was then uplifted and the stress was unloaded back to this point here. We would then have a overconsolidated soil And we could do an odometer test from point F, and the curve we would get is F, G, E. And you notice by the time it gets to point E, it's almost asymptotic to this line here. There's not a sharp change of curvature where the reloading curve rejoins the virgin consolidation curve. And if this is what you had got in your odometer test, you would be tempted to think that there's a pre-consolidation pressure somewhere here, which clearly is definitely not the case because it has been pre-consolidated up to this pressure here. Once you consolidate or over-consolidate a saw to a really high stress and then it is uplifted, you'll never get from an odometer test a yield stress. You may get a curve like this, but you won't get a yield stress because the time you get back to this point here, the thing is almost asymptotic to it, so there's no sharp change in curvature at that point there. So that's the traditional portrayal which you find in textbooks, and students learn that you have this compression index CC and you have a set of parallel lines here, the slope of which you can portray using a log scale as the swell index CS. There is, of course, an alternative way expressing compressibility, the method that I mentioned in part 1 at the very start, really, of giving students an example of estimating the settlement of a layer. It's a very simple parameter that's sort of akin to the Young's modulus of elasticity theory, except it's up the other way and it's one-dimensional, so it is slightly different. This is Yanbu. He has been saying these things for a long time. I took this from one of his publications in 1998. It is very surprising, to say the least, to absorb all the efforts still made internationally in studying remolded clays. If the aim of such research is practical application, it's obviously a total waste of money. And further on, it remains a mystery why the international profession still uses the awkward E log P plots and the incomplete and useless coefficient CC, which is not even determined from the measured data, but from a constructed line outside the measurements. I'm not going to solve the mystery, but I'm going to illustrate graphically the point that Yanbu is making here. These are the results of an odometer test on a moderately over-consolidated, I think, a Pleistocene clay from here in Auckland. So this is a standard plot here, and we've taken it up to a fairly high stress, a bit over 3000 kPa. Now, not all odometer tests are taken that high. If we do take it that high, this section here does look fairly straight, so we're not actually using a line that's totally outside the plotted data. But if, as is normal with odometer tests, only go up to 700 or a bit over 1000, then you're going to put a line here which is tangential to this line, and the slope of it is going to be different from this line. You can also determine a CS value from this line here. The stress range you're likely to be interested in designing a foundation on a residual soil in particular, or soil of this type, of moderately over-consolidated sedimentary soil, probably you're talking about 100, 200, maybe 300 kPa. So that's the compressibility of the soil that you're interested in here. So those two coefficients are totally irrelevant and completely useless as far as doing an estimation of settlement is concerned. That just reinforces the point or illustrates the point that Yanbu was making. If we replot this on a scale down here, you'll see that curve, which quite a smooth curve coming around here, curves now in the other way. The little section that we're interested in for our foundation design is not far off linear. And on the next graph, I'm going to have a look at a standard portrayal in textbooks of the Casagrande construction for estimating the pre-consolidation pressure. There are 4 of them here. The bottom one is actually from my textbook, which is a bit of an embarrassment to me, and I'll simply have to wear that. But if you look at the way these are taken straight from the textbooks, Craig's, Woodall, Das, and mine, you can use the Casagrande construction to get a pre-consolidation pressure on all of them. But when you replot that on a linear scale, the picture is totally different. There's really no evidence at all that this pressure here is anything other than a feature of the way the data are plotted and the way the Casagrande construction is applied. There's no relationship between that pressure there and any change in the compressibility of the sample. None of the linear graphs show any sign of a pre-consolidation pressure. This is just a graph, actually. It's fictional, really. It's not an actual test. But sometimes at conferences, I saw this recently, I think at the Paris International Conference, a presenter talked about at the onset of yield, indicating this part of the graph. Now this graph here, plotted over here, is this graph here, is this material here on a linear scale. So there's no indication whatever that this is anything remotely like a pre-consolidation pressure or a yield pressure at all. There is a point, however, that point B here, when the soil starts to stiffen up. So the first part is pretty well linear. From this point onwards, it starts to steadily become stiffer with increasing pressure. This is fairly typical of quite a lot of stiff soils, actually, that they're reasonably linear for a while, and they start to stiffen up as the effect of the compression or the pushing together the particles takes over and the soil becomes less compressible. So only point B on the linear graph indicates a change in compressibility. It's the start of what we call strain hardening. These are graphs of a tropical red clay. In fact, it was the first clay I ever had a careful look at the graphs for when I started working for the Indonesian government in that 1960. I started work there, and I was puzzled at how smooth this curve was. There was no sudden change in compressibility, and I looked further into this and took some very careful undisturbed samples and repeated these three tests here, and again it came out with this very smooth curve without a very sharp change in curvature. I mean, you could apply the Casagrande construction here and kid yourself that there was a pre-consolidation pressure here. If we plot this data on the linear scale, we get these graphs here. And if we have a look at the graphs over the stress range that we're interested in for design, we get those graphs there. So we're not likely to be applying a foundation load more than, or certainly on the tropical red clay, you might go up to 200 kVA. But I think you would agree that if we simply draw a straight line from the starting point down to this point here and calculate the EMB value, that would be a very good representation of the EMB value. So the lines are close enough to straight lines to use the constant EMB value over the stress range that you're interested in for foundation design. Again, this is the top graph here is taken from an ISSMGE publication some years ago, and they are tests on samples from the Piedmont Foundation in the southern states of America. I know nothing about it other than the fact that these samples were taken and these graphs were plotted, and from them the pre-consolidation pressure was estimated. The authors admitted that it was a little bit arbitrary trying to estimate the pre-consolidation pressure from graphs like this, but they did go as far as calculating these over-consolidation ratios listed here. If this data is replotted, then you simply get curves in the opposite direction, concave from above, whereas these ones are concave from below. It's a further example of linear versus log plots. The log plot, as I said, is routinely misinterpreted. This was taken from an ISSMGE paper. Again, test on our Auckland clay. This is a different clay to the one I mentioned before. This is weathered from soft sandstones or mudstones. And you look here, you would be tempted to think that there was a pre-consolidation pressure here, but if you transfer this to a linear scale, then there's no sign of a pre-consolidation pressure. There's a bit of a change in compressibility here, which I suspect is really a feature of setting the sample up, a bit of sample disturbance and bedding in the porous stones. I think I would draw a straight line or an average straight line through these and ignore the fact that it has not been a soil property, just an experimental characteristics there. But as it shows there, there's no evidence of a pre-consolidation or a yield pressure. These are graphs from volcanic ash clays, andesitic ash, which I'm fairly familiar with. And it's quite a variable material, depending on how the material, of course it's all airborne and being deposited, how the weather and the climate is at the time of deposition, I suspect, because you can get void ratios as high as 4 or 5. These ones are from samples from the same formation at varying depths, with a void ratio of about 3 and 0.3, something like that. Way down here it's only just about 0.1. Looking at these, you would be tempted again to think of a yield pressure or pre-consolidation pressure somewhere here. But when these are replotted, we get these graphs here. The only one that shows a clear pre-consolidation pressure is this one here, or a yield pressure. I shouldn't call it a pre-consolidation pressure because it's got nothing to do with consolidation. It's the way in which the material is weathered into this allophane clay. Allophane is a very special clay mineral you find in andesitic soils. So the log graphs, as always, suggest a similar pattern of behavior, and I think that's one of the greatest defects of the E log P plot. Everybody has this idea in their mind that you've got a certain compressibility and that it increases when you curve over onto the latter part of the curve. So it is embedded in people's mind that you can portray the compressibility of soil with 2 approximately straight lines. When you plot this data on a linear plot, you'll see that the behavior is quite different. Only this one here shows a yield pressure. B more or less a straight line, and C sort of steadily becoming stiffer as the load applies. The linear graphs show that there is no pre-consolidation pressure. Only one sample shows a yield pressure. One more or less linear, one is strain hardening. And I think if you're going to present a figure to your students, this is a far more appropriate graph to present than the traditional graph with the log scale. This one gives you a genuine picture of the range of behaviors. Well, there may be more behaviors than this. The range of behaviors you get with various types of clays. So to summarize, there's no sound basis for portraying the compression behavior of residual soils using a log scale for pressure. The continued application of the E log P plot to residual soils and indeed to sedimentary soils is a source of routine misunderstanding. A more appropriate way of illustrating the compression behavior is by using a linear scale. And the linear parameter MV is much more appropriate and much easier to use in expressing the compressibility of soil and in doing estimates of settlement. As I've summarized here, for settlement estimates, with soft, normally consolidated clays, the log parameter CC is appropriate and should be used for all other soils, including over-consolidated or medium over-consolidated sedimentary clays. The linear parameter MV is much more appropriate. If all practicing geotechnical engineers and all teachers of soil mechanics always plotted the compression graphs using a linear scale, as well as the conventional log scale, then use of the log scale would quickly fade and almost come to an end. The second part of this on the compression behavior is to do with the rate of consolidation. There are 2 issues. One is the determination of the CV parameter from odometer tests. The second one is the determination of the drainage path length for calculating the settlement rate of a surface foundation in particular in the field. The first one is mostly relevant to residual soils because they got relatively high permeability and relatively high CV values, but the second one is valid for all soils. So the first issue is having a look at the consolidation rate. These just shows the theoretical graphs you should get from an odometer test with a sample thickness of 2 centimeters and porous stones above and below. And these are the values of the CV value with factors of 10 in between them. For many residual soils, you're likely to get behavior like this. One is volcanic ash clay, one is our Auckland clay, and one is tropical red clay. So the rate of consolidation or compression is extremely rapid. I thought when I originally encountered this that maybe the soils weren't fully saturated. So I did get some samples of volcanics in New Zealand. We've got volcanic areas. Some samples there, and got one of my students to do a pore pressure dissipation test by setting up a sample. I think it was about 12 centimeters high or long. So the ratio of the drainage path length was 12 centimeters to 1 centimeter. So the square of that 144. So you would expect it to slow down the rate of consolidation by a factor of 100. And that we would, in that case, be able to get some tidy straight lines when the data was plotted against the square root of time. That didn't turn out to be the case. When we opened the valve at the top of the sample and to watch the pore pressure dissipate as it drained from the other end, the pore pressure disappeared almost as soon as we opened the valve. The permeability was clearly the factor that caused this very rapid compression. We used back pressure to make sure that this sample, I think we did it on several samples, that the material was fully saturated, and it satisfied us very clearly that the reason for this was because of the high permeability of the material. So those curves are really representing just the creep behavior of the material when you apply a load. They don't tell you much about the CV value, but they do tell you that it has a value above a certain limit. If you do an investigation of the odometer test, you'll find that there's an upper limit to the value of the coefficient of consolidation that can be measured in conventional consolidation tests. And this limit is about 0.1 meter squared per day. That's the center curve of those curves I showed you a moment ago. By the time you get down here, it's happening so rapidly that you're not going to get reliable information about the rate of pore pressure dissipation. And the next issue, well, just go back to this for a moment. It's not the case that your odometer test is then useless, because it is telling you that your CV value is high and it's above that value there. So if you use that value to estimate your rate of settlement, you can be assured that the expected rate, at least in theory, will be greater than the value you get using that value there, that it will consolidate more rapidly. This is the second thing I want to look at. Estimating the rate of consolidation of surface foundations on clay, because textbooks and soil mechanics courses normally only cover one-dimensional consolidation, which cannot be applied to a surface foundation. What do geotechnical engineers do in this situation? Well, I've found that more than a few just go on using the one-dimensional charts. Not surprising, as that is all their teachers taught them in many cases. That's the two situations. Here we've got a uniform load over a wide area, and we've got a known impermeable boundary down here, or possibly a permeable boundary, but the situation is one-dimensional, so there your Terzaghi equation applies. When you've put let's say a concrete foundation on the surface here, you've got an impermeable boundary here, so you're going to create consolidation. The consolidation itself will be more or less, the compression will be more or less in the vertical line, but the flow direction will be somewhere out to the sideways here and possibly up towards the surface. So in this case, there is in fact a solution worked out by Davis and Paulus of Sydney University and published in Geotechnical in the 1970s. 1976 there. I've replotted their curves to make them a bit easier to use. These are in my textbook, the textbook called Fundamentals of Soil Mechanics for Sedimentary and Residual Soils. So the difference between these, and indeed Davis and Paulus's and Terzaghi's, is that the length dimension that I've used is a dimension from the foundation, not a dimension from the depth of the underside of the foundation down to the impermeable layer, simply because with residual soils it's pretty difficult to determine a clear boundary somewhere down here. There may be just a gradual transition from soil to rock or something down below, whereas your foundation dimension is fixed. So they're very similar to the ISSMGE charts. For example, if you want to work out the degree of the settlement at a 80% degree of consolidation, you run along here, you've got your value of H upon B you still have to do a guess of this one. So you can run along here and you can get a value of the time factor T, and if you've measured your CV value, you can work out your time to that degree of consolidation. So they're very easy to use. These graphs here are for a strip and a circular footing and for a foundation with an impermeable base. Occasionally you may have a permeable base, so they are also available for a permeable base, again for strip footings and circular footings. The time where you're going to have a foundation with a permeable base is when you build storage tanks, and storage tanks often tend to get built close to harbours where they're on deposits of soft, normally consolidated clay. So you put a good thickness of granular material on top of it before you build your tank. So in that case you have got a permeable boundary at the top, and the rate of consolidation will be much more rapid than was the case with the impermeable foundation. Again, the way of using them is similar. Just a good thing is to give your students some idea of the accuracy of settlement estimates. As I've said, somewhere in their courses, students should be made aware of just how approximate most deflection calculations are, especially estimates of settlement. The following is more or less what I taught my students. With surface foundations on residual soils in particular, or probably firm over-consolidated soils, actual settlement is usually less than predicted values, possibly in the range of about a half or 2/3 of what you predict. And there are reasonable case records of measurements of structures on residual soil showing that to be the case. I think with fills over a wide area of soft, normally consolidated clay, the settlement should normally be quite reliable. I would say not more than 20% or above the estimated value. Yeah, your estimate should be not more than about 20% above or below the field value. The other thing of interest, it's always useful to have a few empirical correlations. One correlation is that if you put sand fill or gravel fill, any sort of fill on top of a normally consolidated clay of reasonable depth, 10 or 15 meters or something, you can expect to use up about 33% or 50% of the fill height with consolidation. If you put on 2 meters of soil, you're going to lose somewhere up between about 3/4 of a meter and 1 meter of consolidation. Finally, estimates of the time rate are not very reliable at all. They could be in error by an order of magnitude, and I think most people are aware of that fact, particularly with soft, normally consolidated soils. Difficult to pick up the presence of thin silty layers or thin sandy layers. You can pick them up sometimes with a carefully calibrated cone, and a few blips in your CPT data will pick them up all right, but that's a general indication of the reliability or otherwise of magnitude of settlement and time rate of settlement. Now, just a couple of examples for teacher-class interaction when you're teaching settlement and consolidation theory. We've got a uniform layer of clay here over a wide area. We've got a uniform stress at the surface, an impermeable boundary here, and for this case, this is the curve we get. We'll now move on and ask our students what happens now. At the bottom here, it's no longer an impermeable boundary, it's high permeability sand. So our drainage path, give your students a while to think about this, but the drainage path length is now half that what it was here, and the ratio is the square of the drainage path length. So the settlement here is going to be 4 times faster than here. So at each point here, you're going to have to move this back to 1/4 of this distance here. It's going to consolidate very rapidly. It's going to come down around here because you're going to divide this by 4 to come back to here, to a point somewhere here. Now we've got the same clay layer, the same boundary conditions as the second case here, but we've doubled the load. So in that case, you've got this graph we already drew here for case 2. You're simply going to have to extend that downwards by a factor of 2 because your settlement is simply linearly proportional to the stress. And I'll leave you to think about case 4 where the graph would lie with that one there. One more example is this one here. We've got a wide site, it's crowded together here, but we've got a wide site, one end of which is twice the soft layers, twice the depth of the layer here. So we've got a uniform layer on the surface, and we've put a settlement marker here and a settlement marker here. And from settlement marker A, we've got this blue line here. So what's the line going to be for this settlement marker here? You might be tempted to think, because there's a lot more compression going on, it might be possibly option C. Because there's a lot more water to drain out, it might be slower than the curve at settlement marker A. But if you think about it enough, well, not enough, just think about it at all, how the compression, the consolidation actually occurs. It starts from the surface. If you think of those pore pressure contours, they start up at the surface here. So initially, you see, compression is only occurring at the surface. And the rate of compression here and here knows nothing about the depth of the layer down here because the water is only draining from up here. Once drainage starts to occur from down here, then there will be no further water coming from here, but there will be from here, so it will slow down. So there is a point here, so the answer for this point here is that your curve will be the same as the curve for, this point will be the same as for the first point, and then there will be a point here at which it departs, the point at which water is flowing up to the surface reaches this depth here. And from that point onwards, the curve from here will deviate down here. And of course, we'll end up somewhere to the right of our picture here at a thickness double this one here if we assume our soil is linearly compressible. It's useful to make connections between things, and I'll just talk briefly about a couple that I think are worth making. Seepage and consolidation. The Laplace equation and the 1D Terzaghi consolidation are usually derived quite separately in classes or in textbooks, and students are left unaware of their close connection. By considering transient flow in 3 directions, we can obtain that graph there very easily. It's the same process you use for determining the one-dimensional Terzaghi equation, except we've got flow in 3 directions. The Terzaghi equation is slightly different from this because we've turned moved the parameter over to the other side and given it a CV value. But that's the general expression for transient flow in 3 directions in a uniform soil. And if we want to derive the Terzaghi equation, then we're going to just get rid of 2 dimensions, get rid of our x and our y, and just leave down, and that now is our Terzaghi one-dimensional consolidation equation. If we want to get a steady state equation, then we need to put our delta H by delta T equal to 0 because the head is not changing with time, and that leaves us with the Laplace equation for 3 dimensions, or if we can drop up 1 dimension and we get the Laplace equation in 2 dimensions. And in terms of shear strength and stability analysis, particularly when you're introducing bearing capacity, retaining wall design or earth pressures, stability of slopes, they are all stability issues. And all 3 involve similar methods of analysis, consisting essentially of identifying a failure mechanism. involving a block of soil and then analysing the forces acting on it and introducing the shear strength of the soil into that. So it's a limit equilibrium thing we're looking at, the stability of these various failure mechanisms. The mechanism here is really defined by theoretical concepts, so that's a fixed mechanism there. Here we normally assume that it's a straight line. That's not quite correct, but it's pretty good. But we don't know, except in the case of a level site and a totally uniform soil, we don't know exactly at what angle it will be, so we'll usually be using the Cooler method and doing a series of trial wedges there. And when we come to the natural slope, then our mechanism is to assume that our soil is reasonably uniform, and we assume a circular arc. If the geological conditions are different, then we might like to use a non-circular analysis. But again, we're analysing the stability of this block of soil against moving down on that slip surface there. And it's good, I think, to do this together, introduce these together, and then think about how to apply the safety factor to these situations, because there are differences in the way it applied. I would always start at this one here, because you can then use the Bishop equation quite readily, that Bishop defined the safety factor as the factor by which the peak strength would be divided in order to give you the mobilized strength on your slip surface or your slip plane. That was Bishop's definition of the safety factor. There are there are alternative ways of introducing the safety factor to this analysis, or to this one. I am aware of modern limit state methods where you're using strength reduction factors and load factors and things like that, but in the initial stages of teaching the servants, I think it's very preferable to use the concept of a simple factor of safety. Just a note about soil compaction. I shouldn't spend a lot of time on this, but I just want to make the point that while we are very familiar with the Proctor test, the Proctor test has proved its worth over the years. These are typical Proctor curves, one for the standard compacted effort, one for the modified compacted effort. I just want you to note that at the optimum water content, the air voids are generally around the 5%. When you move a little bit up here, and you may allow the contractor to come distance up here, you may be approaching 8 or 10%, but there is a relationship between the air voids and the water content, or the optimal water content. There are difficulties in applying the Proctor method, and those difficulties are extreme variability of some soils. Occasionally there is no clear optimal water content, fairly rare, but it does happen. If you want to compact your soil at its natural water content, which is what we would all like to do because we don't want to waste money drying it out, and sometimes, in fact, the weather conditions are such that it's almost impossible to dry the soil. So we should be aware that if we're trying to compact the soil at its in situ water content, highly structured soils become progressively softer with increased compactive effort. The more you roll them, the softer they become, simply because you're remolding them and softening them and releasing water in the void space, and they become softer. That's an example of the variability you can get on some sites. These are on single sites in the Auckland area here. These are from Pleistocene deposits. These are from weathered volcanics, mostly basalt and volcanic ash. But you can see the huge range of Proctor tests from those small sites. So to do a quality control with soils such as this, you would have to do a Proctor test every time you do a control test in order to know what you should compare your control test with in terms of its water content and the desirable water content. And this is just an example of this very unusual clay mineral called allophane. If you have clays with a high allophane content, if you air dry them or put them in the oven, you change their chemical composition, and it's irreversible. If you take a sample of allophane clay, volcanic ash clay, and manipulate it in your hands, it's quite plastic, it's a clay. if you put it in the oven, leave it in the oven and take it out, no matter how much you wet it up, it won't revert back to here. There's a reversible change goes when you dry it. So you're going to get quite different compaction curves after you have dried it out. So in this case, this is the curve you will get. These are all individual tests, all individual samples. We didn't get our drying quite right to get them even, but they were simply spread out on trays, and we weighed them on a balance and put them back in a plastic badge each time, and then did the test. Then we redid the test after air drying, leaving it in the laboratory bench for a week or two until it was thoroughly air dry, and again after putting them in the oven. So you'll see how dramatic the change in behaviour is. Again, down here we decided we'd have a bit look at not drying it all the way back to air dry, but to this point here, and you can see the chemical change has already occurred, so you don't have to dry it out very much from its natural water content before it gets changed in composition. This has caused various contract disputes over the years because consultants unaware of or geotechnical engineers unaware of the strange behaviour of alpine clays will allow the laboratory to do a conventional laboratory test, which is done most easily by drying the soil back and then adding water to it to get your range of values. So your laboratory may give you a curve of this sort here, and then the consultant will write a specification identifying an optimum water content here and identifying a maximum dry density. The contractor will dry the soil back to that range there that the specification requires, and then compact it and find he or she is totally unable to achieve this density up here, this dry density up here. That's been a source of dispute situations when people have been undertaking earthworks in allophane clays. But again, you can see down here there's hardly an optimum down here actually. But you can actually compact these soils. Often they occur in places where the climate is too wet to do much drying, so you sort of put aside your proctor idea and you do some field trials and compact the soil lightly. Don't bring in sheep's foot or heavy vibrating or steel wheel. Compact it lightly with tracked bulldozers and things like that, and just squeeze the soil together and do some field trials. You'll find that you can find a way of compacting it down here at its natural water content, but you have to be careful not to over compact it. If you give it too much, it just softens. So it's important to recognize that compaction of a soil can have two effects. It can densify the soil, that's what we hope it does, and by densifying it, making it stronger. But most soils are somewhat sensitive, so remolding the soil can well cause it to soften. As I've said here, most natural soils lose some strength on remolding, and compaction is a form of remolding. Compaction destroys bonds, crushes particles, and releases water trapped in the structure of the soil and makes it softer. This is a nice bit of work some Japanese researchers did quite a long time ago. They've taken a range of volcanic ash soils or volcanic soils from Japan, and they've done tests with different numbers of Raman blows. They're all separate points from which they've extracted this information, and you'll see. And they've just got a penetrometer to measure the strength. You needn't worry about the actual value of this, but this is a measurement of the strength. So in this case, and in this case, the strength did increase and then it started to decrease. But for most of them, the strength decrease has begun almost right from the beginning. As soon as they were giving a certain number of blows, they were softening the material. So quite clearly, there is what I would call an optimum compactive effort. The soil is not something you can easily identify, but you can get an indication of it by doing compaction tests in the laboratory. But in these sorts of cases with volcanic ashes, you really need to do some trials in the field to identify the best way of compacting them. I think the thing that students should understand is that, sure, the proctor's been around for a long time and it's proved to be very valuable, but it's actually not measuring what you're after. You're not after a certain water content, you're not after a certain density. What you're after is a strong material and one that is of low compressibility. So the alternative, which we've developed in New Zealand, is an alternative method, and the basis of it is this, that the undrained shear strength of a clay at the standard Proctor water content is normally in that range. If you go back to my part 1, you'll remember a graph showing the relationship between the undrained strength and the plastic and liquid limits of the clay, and at the plastic limit the strength was about 200 kPa, so that tallies because your plastic limit is fairly close to the standard Proctor optimum in most moderately to highly sensitive clays. So that's one point of interest. The second one is that the air voids in a clay compacted close to optimum is the point I already made, about 5 to 8%. So controlling the undrained shear strength and the air voids will or can produce a fill of similar characteristics as the conventional method of compaction control. The strength limit, if we say it must not be weaker than 150 kPa, that prevents the soil being too wet. And if we specify the air voids not to be greater than, say, 8%, it stops the contractor compacting it too dry, because if it's too dry, it simply won't compact down to give you a low air voids. This is a graph showing that relationship between undrained shear strength, done in the course of doing a Proctor optimum test. And the measurements were done both with a hand vane, just poking it into the end of the mould, and taking small diameter samples out of it and doing unconfined compression tests. It's a fair gap between them, but you can see at the optimum water content, the undrained shear strength is in that range I mentioned, somewhere around about 150 to about 200 kPa, or a bit more, 240 kPa. So that's just emphasizing the fact that with your conventional method, you've got definite limits like this. A dry density method, an upper limit to your water content, a lower limit. With your, sorry about that, with your shear strength and air voids, it puts an upper limit here. There will be a water content here at which you can't achieve the required shear strength. There isn't a clear line here. It's simply the fact that the contractor won't be able to achieve this air voids limit, trying to compact the soil to dry. So it does achieve, as I see it, a fill of the same standard or quality as you get if you're doing it according to the Proctor method. These are the values we normally use in New Zealand. An undrained shear strength not less than 150 over an average of 10 tests. Minimum single value down to 120. Air voids for normal soils, 8% is about right. With high content allophane clays with very high void ratios, I think we've had to push it down to about 10 or 12% because the contractors haven't been able to get it done below about that. And the control measurements, the shear strength is very easily done. Hand vanes are the simplest, but you can do the simple penetrometers and things like that. Unfortunately, the air voids still have to be measured in the usual way, but the point I would make in relation to countries like New Zealand or Indonesia or Malaysia, because of their temperate climate, plenty of rainfall, it's usually the case that the soil is on the wet side of optimum. So it's really the shear strength that has to be controlled. The air voids will normally be achieved without any difficulty at all, but the shear strength may be difficult to achieve in certain situations. The advantage with using the shear strength is that the contractor can go around with a hand vane, doesn't have to wait for the consultant or the test laboratory to come along to check whether he's achieving the specification or not. The contractor can walk around the hand vane and do the tests themselves. That's the big advantage of it. Actually, I think anybody who's ever done controlled an earthworks operation using the shear vane and the air voids would never go back to the Proctor method. So those are the tools. There's a Pilcon type vane, I think we used to call them. We have a penetrometer called a Scala penetrometer like this. US Army Corps of Engineers used a penetrometer like this, calibrated against CBR, so there are a range of tools available. The advantages of the shear strength and the air voids are these, that the specification is constant regardless of the change in it. That's the big advantage of it. You don't have to do proctor test at all, really. You can simply write the specification and control it. Control testing is more straightforward, particularly when the general trend is for the soil to be a bit on the wet side of the desirable water content for compaction. The specification is easily varied if different characteristics of the fill are required. I was one time temporarily the site engineer on a geothermal site in West Java in Indonesia, and the contractor was forming a level area. This was on a volcanic clay site. It was a level area, not for the power station. That was on a raft, but this was for the transformers and all that switch gear. So it's quite light gear, but the contractor was having trouble in achieving a undrained shear strength of 150 kPa. In fact, the contractor could hardly achieve more than about 70 kPa. So I lowered the specification from 150 down to 70 and was very comfortable about that for two reasons. Firstly, because the equipment being installed there was very light. And secondly, 70 kPa is quite a useful figure to have in your mind. If the shear strength is 70k or above, you can normally drive an ordinary car across it without indenting the surface or damaging it. So the contractor had to be aware of that fact, that he couldn't bring particularly heavy equipment in there if we went for the 70 kPa. So let's move on from there. Some comments on the limitations of theory. Students should be encouraged to recognize that theory does not have the same omnipotence in geotechnical engineering that it does in structural engineering. This does not mean that a thorough understanding of basic principles is not needed. It is a fundamental need. These are Terzaghi's words from his address to the First International Conference in Harvard in 1936. However, as soon as we pass from steel and concrete to earth, the omnipotence of theory ceases to exist. In the first place, the earth in its natural state is never uniform. Second, its properties are too complicated for rigorous theoretical treatment. Finally, even an approximate mathematical solution of some of the most common problems is extremely difficult. I think the most convincing illustration of the limitations of theory is the behavior of natural slopes, especially those in residual soils. These are just a few pictures of, in this case, highway jobs that I've been involved on. That's weathered sandstone in Malaysia, and you can see a slip on the left-hand one has occurred on a pre-existing plane here. That was clearly a pre-existing plane, which you are very unlikely to identify in your site investigation. This is weathered schist. One of the interesting things about this particular highway was that there were a lot of cuttings, but most of the slips weren't occurring at the top. They were occurring halfway down the side or even towards the lower points, so they were occurring down in the valleys rather than up on the ridges. I think it's because of the way the water is shed from up here and tends to concentrate down in the lower levels here that the slips were occurring in those positions. Again, another couple of positions. This is again on that same highway job in Malaysia, weathered sandstone. You would have thought that that face there would have continued right up to the surface, but for some reason that piece fell out. This one here is slightly interesting because this is weathered volcanic ash, high elephane content clay. It's normally a good material, and it will stand up very, not close to vertical, but it will stand up at about 70 degrees to maybe up to 8 or 10 meters high. The problem here arose simply because this is Laha flow material down here, and it's been weathered with geothermal seepage coming through here, high temperature. So this clay down here is high in montmorillonite content, quite different from this here. Again, I mean, this wasn't a major rate, it was an excess rate to the geothermal plant, but again, they did have a bit of trouble having to cart this material away. And lastly, another one here, or two more here. That's weathered sandstone again in Malaysia. This is weathered granite. Weathered granite is rather interesting, but it's troublesome. It stands up all right, but it is terribly erodable. Vast quantities of material have been eroded from these cuts made in weathered granite in Peninsular Malaysia. And a last one here, this one here shows you again what you're up against with residual soils. It's a newly made cutting, so we couldn't judge how long it was likely to stay in that shape. Actually, when we inspected it, it had only been done a few weeks, I think, when we saw it. But you can see the variability of the material. There seems to have been a valley here, and then there was some other material upon it, another valley here that became infilled in due course. It was a major energy project, and the object of the highway was to be able to transport heavy gear from the lowland area up into the highland area where the project was. It was impossible to think that we could have done any slip circle analysis or any sort of analysis. It was all a matter of judgment. I think I and two other people, one another engineer and one a geologist, spent about 5 or 6 days trekking through the jungle and inspecting whatever cuttings we could find. As I've said here, visual observation was our main evaluation tool, and our main piece of apparatus was the helicopter that would pick us up and drop us off wherever we wanted to, whichever route we chose to inspect on a particular occasion. The pictures above emphasize the difficulty of applying analytical methods to natural slopes. However, I would say there are some natural slopes of sufficient uniformity that analytical methods may be appropriate. And this is interesting, I think, too, that many textbooks, to their credit, give appropriate warnings about this issue, and teachers need to do the same. This is from Budu. Geotechnical engineers have to pay particular attention to geology, surface drainage, groundwater, and shear strength of soils in assessing slope stability. However, we are handicapped by the geological variability of soils and methods of obtaining reliable values of shear strength. The analysis of slope stability are based on simplifying assumptions, and the design of a stable slope relies heavily on experience and careful site investigation. This is from Das, I think an equally good warning. The stability analysis of a natural slope is difficult to perform. Evaluation of variables such as the soil stratification and its in-place shear strength parameters may prove to be a formidable task. Seepage through the slope and the choice of a potential slip surface add to the complexity of the problem. I think that's another good warning. This one, I think, is a much less satisfactory view. In contrast, slides are very amenable to quantitative analysis. Geotechnical engineers have developed methods of evaluating the potential for failure and can express it as a factor of safety. These methods have proven to be reliable and are used routinely in geotechnical engineering practice. Now, I couldn't agree with that at all. For me, an inspection of the site, a visual inspection, is of far more value than any number of slip circles, etc. 2 further important points. The situation with constructed slopes, such as embankments and earth dams, is totally different. There should be no obstacles to applying analytical methods. In this case, the materials and their properties are now in the control of the engineer, as also is the seepage and the pore pressure state. We can put in cut-off drains, interceptor devices, and control the pore pressures that are going to rise in any particular embankment, water retaining embankment. The limitation of theory in the example of the natural slope arises because of the variability of the soil properties. However, it is also the case that even with totally homogeneous soil conditions, theory does not produce valid answers, and the following slides illustrate 2 important examples. The first one is a vertical bank, especially the sides of a vertical trench. This is a matter of life and death, as fatal accidents involving the collapse of trenches occur far too often, and they occur worldwide. Students should be made aware that theories about the critical height of vertical banks in clay, particularly the banks of trenches, have no practical value at all. I think you already have got the message. Can geotechnical engineers predict the stability of vertical banks in clay? Soil mechanics textbooks generally give the following expressions for the maximum height of unsupported vertical banks in clay, what they call the critical height. Some people should say that you can argue that this value should not be 4, it should in fact be 2. But I think most textbooks equating the value of 4. So that's the formula in terms of effective stress. This is in terms of undrained shear strength. These expressions are of theoretical interest only, and very rarely, I think never, are of practical relevance. Unfortunately, the cold hard fact is that this is one area where geotechnical engineers cannot provide reliable answers. Neither theory or experience can ever enable reliable predictions to be made about the height or the length of time at which a vertical clay bank will remain stable. And if we take a typical soil with these properties down here, undrained strength of 100, unit weight of that, C and phi like that, typical of reasonably typical of the many residual soils that I've been involved with, and apply those standard formulae, you'll come out with this. For a total stress analysis, you'll get a critical height of 24 meters, divided by a safety factor of 3, and you come out with 8 meters. If you do your analysis in terms of effective stress, you'll get a depth of 7.2 meters, and with a safety factor of 3, you'll get 2.4 meters. Most authorities who govern the safety of workers require that workers may not work in a trench. Some use 1.2 meters, some use 1.5 meters. If they're going to go in trenches any deeper than that, they must have proper support systems in place. So as I've said here, theoretical heights are quite unrealistic. Site safety authorities limit the height of banks or depths of trenches where people work generally in the range of 1.2 to 1.5. I think 1.5, even 1.2, if it was a soft clay and you were bending down, putting the ends of a pipe together, I don't think I would be wanting to work in a trench. I suppose I could make the observation that you have some chance of survival if you're alongside a vertical bank, but if you're in a trench, they are death traps. They won't push you sideways, all they do is trap you in there, stop you from breathing and whatever, or they bury you. So they are death traps, and geotechnical engineers should be very aware of that fact. Particularly teachers who don't teach those critical height formulas as if they have the same validity as the other material you teach. Make the students well aware of the fact that regulations are quite rightly in place that people may not work in trenches deeper than those values I've quoted. That's a very sad collapse of a trench. I think the body is still there, but just out of sight. I was really involved in a court case where the Crown were prosecuting the contractor. And a bearing capacity issue. This is an interesting one. Consider the bearing capacity of soft clay according to total stress and effective stress analysis. These are parameters. I think I got these from the clay I did my PhD on the estuary of the Thames estuary, the north side of the Thames estuary. A total stress analysis is just for simplicity, we put it right on the surface. Is that value there? Your undrained shear strength, multiply a bearing capacity factor, and I think for strip footing it's about 6.3, so we come out with about 75 kPa. That's the ultimate strength. The effective stress analysis comes up with this formula here, 120 plus 33.6 B, where B, this is a circular foundation apparently, where B is the diameter in meters. And those are the graphs. So your total stress analysis is giving you a value which is independent of the breadth, whereas your effective stress analysis gives you a value which rises very rapidly. Well, I don't think any geotechnical engineer would consider designing their foundation on anything other than the undrained shear strength. And the values that you get from an effective stress analysis are quite unrealistic. This formula gives you a value far higher than the undrained value, and clearly unrealistic. Nobody would dream of putting those sorts of stresses onto soft, normally consolidated clay. Lastly, a comment on what not to teach. The simple answer is not too much, in the sense of trying to cover too wide a curriculum. The aim should be to produce graduates who at least have a sound grasp of the fundamentals of the subject. I will make a comment on critical state soil mechanics because I do a bit of teaching or lecturing in Chile and South America, sometimes in Colombia, also in Indonesia and Malaysia, and people ask me, what about critical state? Should we be using critical state? Well, I'll just make the following comments. Some universities teach critical state soil mechanics in undergraduate classes. That does not seem to me to be at all wise. It will only confuse students at a fundamental level and not improve their chances of becoming competent geotechnical engineers. And the next slide contains some specific comments on critical state. Critical state is created when sufficient strain or deformation produces a uniform state in the soil in which both the strength and the volume are constant. That's a perfectly valid concept for sand, but seldom for natural clay, because these clays, particularly natural clays, generally fail on distinct planes, and a uniform state does not develop. The strength declines from the peak and heads down towards the residual strength. Critical state has been developed from the study of remolded clay, and totally neglects one of the most important characteristics of natural clays, namely their structure. For design purposes, at least some critical state exponents recommend the use of the strength parameters from the critical state rather than the peak state. I can't see how that can be right, because at the critical state, the cohesion intercept is 0. Many natural slopes are only stable because of their substantial cohesion value or cohesion intercept value. The critical state parameter has found its way into some design codes. And again, this is not sensible, partly because it cannot be measured in clays. As I said, they head from the peak down to the residual strength, and you'll never know where the critical state value is. And partly because stability in most situations that I know of is governed by the peak strength, not the critical state strength. There's some nice work done, I think, at the University of California some years ago. Some testing of reinforced earth walls, and the paper they published clearly came out on the side that the failures that they observed with these model walls were governed by the peak value of phi, not the critical state value. Too much unproductive research into critical state has been undertaken in universities in various parts of the world, including in the developing countries of Asia and South America. Students from these countries return home from some Western universities knowing a lot about critical state soil mechanics, nothing about residual soils, and they undertake research projects applying or trying to apply critical state to local residual soils, only to find that the two are incompatible. Lastly, a couple of comments on the computer. Will computer skills help students become better geotechnical engineers? My answer would be maybe yes, maybe no, but there's certainly not a clear yes to that question. Students should recognize that they will not become good geotechnical engineers by spending a lot of time in front of a computer. Particularly new graduates need to spend time in the field, taking part in drilling, logging, soil sampling, CPT testing, etc. And throughout their careers, they should take every opportunity to observe how soils behave in the field. Assessing the stability of natural slopes will always be more dependent on visual observation than the results of computer analysis, or indeed of any other form of analysis. I did my undergraduate courses using the slide rule, of course, in my day. And in fact, when I worked for a consultant from the year 1976 to 1986, we were using calculators, HP calculators, but we weren't using computers, and we were regularly involved in assessing the stability of natural slopes for subdivisions or for house sites. But we never resorted to analytical methods. It was always a matter of examining the geology, careful site inspection, visual observation of a slope. It's going to tell you more than any amount of testing and analysis. I think that brings me to the end of my presentation. Let's see what's on the next picture. Oh yeah, this is just to amuse you. This is what you get from your computer and put into publication somewhere if you're not thinking about it. This is from a paper giving the liquid limit and the plastic limit. Those values are to the second decimal point. The likelihood that you can measure this even to one figure beyond the decimal point is pretty unrealistic. So there's not the slightest chance that these are in any way sensible. The liquid and the plastic limit are actually defined, they were originally defined by Casagrande as whole numbers, so they should only ever be given as whole numbers, which is a totally sensible thing to do, because there's no way you can measure them to the accuracy of even one point after the decimal, one place after the decimal point. This is a rather remarkable odometer test too. That was actually in the report of a quite reputable company, not a New Zealand company, but a company that operated in a number of countries, and it was put into the report. It was fed out of the computer, and whoever put the report together just put it in. I suspect that they wrongly put that data point there in. I suspect that that point there should have been down here, in which case this curve would have come down to that point there and come back along that line there. But putting a curve like that into a report that's going to be read by lots of people just illustrates how careful, not how careful, but I mean, people are going to dismiss that as a error of some sort. Right, so I think that brings me to the end of my production. Just some closing remarks, putting aside the issue of the material. The basic essentials for effective teaching. Respect for the student on the part of the teacher. I think this is the first requirement to allow the teaching process to function smoothly. Don't talk down to your students, but have respect for every one of your students. And conversely, trust and respect in the teacher on the part of the student. This is something that students have to earn. They don't get it just because of the fact they're occupying, well, not in Western universities anyway. I would think too that teachers may be brilliant presenters, perhaps a little too brilliant, but still fail to win the trust of their students. Students are fairly perceptive in getting a feel for whether the lecturer really knows what he or she is talking about. So that brings me to the end. Thank you for watching this. That's our largest water supply dam in Auckland. It's an earth dam with a vertical chimney drain running along under here. And this is just grass down here, and we keep the grass tidy by grazing sheep on it. These little white spots you see down here, these are sheep. They run up and down here and keep it nicely mowed. And those are the references that I've referred to. That's where that quote comes from. These were both published in that online journal, Geotechnical Research. That's the book that Wiley's published about 10 years ago, which covers most of the material that I've covered in this talk, and probably quite a bit not. So thank you for listening.